Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So question number 1, an insulated rigid tank of volume 10 meter cube. So it is an insulated rigid tank of volume 10 meter cube contain initially 1 MPa and 600 Kelvin. So initial pressure maybe Pi 1 MPa, initial temperature Ti 600 Kelvin. So this insulated tank is connected to a valve. The valve is connected to the tank, is opened and air is allowed to escape. So you have a valve. So here a valve is there. So once the valve is opened, the air will be allowed to escape. Maybe through this, the air is allowed to escape. If the valve is opened, air will be allowed to escape and it is completely insulated. So that is heat transfer will be 0. If it is insulated, the heat transfer will be 0. The temperature inside the tank drops to 400 Kelvin. So the valve connected to the tank is opened and air is allowed to escape until the temperature inside the tank drops to 400 Kelvin. So from this, so a final temperature of the air inside the tank is 400 Kelvin. So until the temperature of air inside the tank is dropped to 400 Kelvin, the air is allowed to escape through the valve. The temperature of the discharge air can be approximated as the average of initial and final temperature. See, there is a air discharge. So the temperature of the discharge air, maybe that we will take it TA, TD, discharged air. Temperature of the discharged air will be equal to T initial plus T final by 2. Average of initial and final temperature of the air in the tank. So that is initial temperature is 600, final temperature is 400 by 2, it is 500. 500 Kelvin is the air which is discharged out. So the air which is discharging out will have an enthalpy. And what is the mass which is, so initially the mass inside the tank will be Mi. So the initial mass of the tank inside is Mi. After the mass is escaped out, there will be a final mass inside the tank. Okay, so the mass inside the tank initially Mi, mass after the temperature reaches 400 Kelvin, the mass inside the tank is Mf. So the energy going out is initial mass minus final mass into the enthalpy of discharged air. So this is the energy which is going out of the tank. Initial mass minus final mass. The difference in mass is flowing out. Since it is flowing, so it has an enthalpy, and kinetic energy and potential energy will be neglected for the discharged air. And it is assuming as an ideal gas, U internal energy CVDT, enthalpy CPDT. So what is the final pressure inside the tank? So initial pressure is this. What is the final pressure inside the tank? So how do you calculate the final pressure? We know that P final, V final is equal to M final R into T final temperature. So volume of the tank. So initial volume, final volume is same. There is no change in volume, 10 meter cube. Initial and final volume is same. So the pressure, final pressure will be equal to final mass by final volume, or R for air is, it is air, right? Air. We know that R for air is, Cp is 1.005. So Cv will be 718 joule per kilogram Kelvin. R will be 287 joule per kilogram Kelvin. Okay, so now R is known, final temperature is known, only the mass of the final mass we need to know. If you know the final mass, then you can get the, for getting the final mass, you apply the energy equation, conservation of energy equation for this control volume. Take, this is the control volume, conservation of energy equation. So here I just write conservation of energy equation. So energy in minus energy out is equal to change in energy of the system. So there is no energy going into the system. So energy in will be 0. There is a energy out. So what is the energy out? Mass, initial mass minus final mass into enthalpy of the discharge. So this is the energy going out. Then change in internal energy. Change in internal energy means final internal energy minus initial internal energy. So this you can take this Mi minus Mf into Hd is equal to this, you interchange, minus Mf Uf. Maybe I just do it in the next page. So the conservation of energy initial minus final mass into Hd is equal to initial minus final internal energy. So this is what we have exactly written from there. Initial minus final into Hd. Okay, so this, we know that maybe we write one more step. Hd is Cpt, D, discharge temperature. This is Cvt initial, Cv U final. So final temperature. So only the final mass is not known. Initial mass you can calculate if you go back. So the initial mass, if you take initial mass, P initial, V initial by R T initial. The initial pressure is 1 MPa, 1 into 10 power 6 Newton per meter squared, 10 meter cube volume by R 287. T initial will be 600 Kelvin. $58.07. Okay, so 58.07 that you can substitute. Initial mass 58.07. Final mass is not known. CPU substitute in joule per kilogram Kelvin. Discharge temperature is 500. You can see that. Discharge temperature TD. This is 500. Discharge temperature is 500 Kelvin. M initial 58.07. CV is 718. T initial temperature 600 Kelvin given, minus final mass is not known. CV is 718. T final temperature 400 Kelvin, right? So only unknown is the final mass. So the final mass, it comes out to be 19.34 kg. Okay, so once we know the final mass, we know here 19.34, R is 287. Final temperature will be 400 Kelvin divided by 10. This will be in Newton per meter square. So we wanted it in MPa. Let's see, first we will two, 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 0, 23.2 Newton per meter square, or which is Pascal. 10 power 6 Pascal is 1 MPa. So the final pressure is 0.222 MPa. So this will be your answer. So your answer is 0.222 MPa. So now we move to question number 2. So a steam enters a turbine at 5 MPa and 600 degrees centigrade. So this we will do it here. The steam entering a turbine. So turbine will be something like this. So this is the entry point. This is the exit point. So the steam enters a turbine at 5 MPa and 600 degrees centigrade. So 5 MPa, temperature T1 is 600 degrees centigrade. Exit as a saturated vapor at 50 kPa. So entry will be superheated. Exit will be saturated vapor. So the pressure at 2 is T kPa. So the turbine gives you work output. Turbine loses heat to the surrounding at 50 kilojoule per kilogram of steam. So turbine 50 kilojoule. So losing heat 50 kilojoule per kilogram of steam. The ambient temperature is 300 Kelvin. So outside temperature, ambient temperature 300 Kelvin. The heat transfer to the surrounding takes place at outer surface of turbine at temperature 450 Kelvin. So this is the surface. Maybe we take, so the surface through that the heat transfer taking place is the surface temperature through which heat transfer taking place is 450 degrees centigrade. 450 degree, sorry, 450 Kelvin, not degree centigrade. 450 Kelvin. $450 Kelvin. The irreversibility per unit mass of steam flowing through the turbine. Irreversibility. So what is asked is irreversibility. Irreversibility is T0 into entropy change of the universe or T0 into entropy generation. So we wanted it in kilojoule per kilogram. So that means entropy generation, we want it in kilojoule per kilogram Kelvin. T0 is in Kelvin. T0 is in Kelvin, so that this product will be in kilojoule per kilogram. Okay. So now we write an entropy balance for, if you take this as the universe, if this is the universe, this is the universe. So entropy change of the universe is within the turbine. So we apply the entropy balance equation. So whatever entropy is generated here is the entropy generation of the universe. So entropy will be generated inside. So entropy in minus entropy out plus entropy generation equal to change in Maybe it is a steady flow device. Maybe we don't. So rate of change of entropy within the control volume. So we will take turbine as the control volume and apply the. We are not going with the concept of entropy, the universe. So universe, you just leave it. Universe. Anyway, universe is the concept which will be giving you an idea that change in entropy of the universe is nothing but entropy generated in the inside the turbine, because we are considering the turbine as a universe. So entropy generation. So what you understand from here, entropy of the universe equal to entropy generated in the turbine. That is what you need to understand. Because only turbine we are considering as the system inside the universe. That means the entropy generated in the universe will be nothing but entropy change of the universe is nothing but entropy generated inside the turbine. So that is what we wanted to understand by the concept of universe. But entropy balance we apply for the turbine. And turbine being a steady flow device, the rate of entropy change of the control volume will be zero, because this will be zero because turbine is a steady flow device. So now we will. So what is the entropy in? Entropy into the turbine. So this S1 is the entropy in. S2 is entropy out. And along with the heat, there is a entropy out. So entropy in will be S1. Entropy out will be S2. Entropy out. Then Q by Ts. Because the heat is going through the surface, going out from the surface temperature is maintained at 450 Kelvin. So heat is going out from a constant temperature point. That means when heat is going out from the constant temperature point, the entropy transfer will be Q by T plus entropy generation is equal to 0, because rate of change of entropy inside the control inside the turbine will be 0 because it is a steady flow device. So now S1. So how do you go for S1? Here it is superheated. S1 is, this is your S1. $7.2605. S1 is 7.2601 kilojoule per kilogram Kelvin. 7.2605, not 01, 05. Anyway, work output doesn't contribute any entropy transfer. That is why work output we are not bothered. Then saturated vapor at outlet, the mass is going as a saturated vapor. So corresponding this will be 7.5931 kilojoule per kilogram Kelvin. So S2 is equal to Sg saturated vapor at 50 kPa, which is given there as 7.5931 kilojoule per kilogram Kelvin. Okay, so S2 is also known. Now we can substitute S1 is 7.2605 kilojoule per kilogram Kelvin. Okay, so S2 7.5931 minus Q. Q is 50 kilojoule per kilogram divided by 450 Kelvin plus entropy generation. So now you got an entropy generation. This equation gives you entropy generation in the turbine, which is nothing but change in entropy of the universe, because we are considering the turbine inside the universe. Point 444 kilojoule per kilogram Kelvin. So now you got entropy generation. Now irreversibility. T0 into entropy generation. T0 is 300 Kelvin. 0.444. 133.2 kilojoule per kilogram. So this is answer, irreversibility. 133.2 kilojoule per kilogram is the irreversibility. Okay, so now we go to the third question. So heat engine receives heat at 1000 Kelvin. So you have a heat engine, 1000 Kelvin. So this will be the high temperature source. Reject heat to the environment. So it is a heat engine. Maybe takes Q1. So it will produce work output. Reject heat at 300 Kelvin, Q2. This we will take it T2. So efficiency of this heat engine is half of the efficiency of the Carnot cycles. That is half of the efficiency of Carnot engine operating between the same temperature. The work output from the heat engine is completely used to drive a refrigerator. So the work output is given to a refrigerator operating between a low temperature. Maybe a low temperature is low temperature and high temperature is atmosphere, same T2. So it rejects heat to this, and this is the heat Q2 dash. Here Q2, here Q2 dash, and takes heat from the lower temperature. So this is T3, which will be 260 Kelvin. So the heat flow for a refrigerator is from the low temperature to the high temperature. High temperature is the atmosphere, 300 Kelvin. So the heat rejected by the heat engine as well as refrigerator is the same atmosphere, which is at 300 Kelvin. Heat taken from the heat engine is at 1000 Kelvin. Heat taken from the refrigerator is from 260 Kelvin. So the refrigerator that steadily removes heat from a cold space at a rate of Q3 is 5.2 kilowatt. And reject heat to the same environment at 300 Kelvin. The COP of refrigerator is equal to half of the COP of Carnot refrigerator operating between the same temperature limit. then the rate of heat supplied to the heat engine is. So what is the rate of heat supplied? So this is the now if you look at that, the efficiency of the heat engine is work output by heat supplied is 0.5 times Carnot efficiency. So T1 minus T2 by T1. So we know that T1, T2, so W1, Q1 will be equal to T1 1000 minus 300 divided by 1000 into 0.5, 0.35. So maybe this we keep it as equation 1. Now from here, COP of refrigerator is Q3 by work input, Q3 by work input, which is equal to 0.5 times COP of Carnot refrigerator is T3 by T2 minus T3. Because lower temperature is the desired effect. So now we know Q3, which is 5.2 kilowatt, work input is equal to 0.5. T3 is 260 by 300 minus 260. So now we get to the work input. So work input will be 1.6 kilowatt. So if work input is equal to the heat engine work output. So heat engine work output from this equation, you know that it is 1.6 by Q1 equal to 0.35. So this will give you Q1 is equal to 4.56 kilowatt. So this is the answer, 4.56 kilowatt. Heat supplied to the heat engine is 4.56 kilowatt. So now we move to question number 4. The steam turbine enters at maybe I just make it here. This is the turbine. So this is entry point 1. Entry point 2. Leaving. Steam enters at 10 MPa 600 degrees centigrade. So P1 is 10 MPa and T1 is 600 degrees centigrade with a mass flow rate. So mass flow rate will be same at inlet and outlet because turbine is a steady flow device. The steam exits to the turbine as a saturated vapor at 10 kPa. So it will be saturated vapor at 10 kPa. So under steady state condition, turbine generates 6. So the work output of the turbine is 16.2 megawatt. So since everything is given in kilowatt and the entropy generation in the turbine is asked in kilowatt per Kelvin, so we will take this as a kilowatt, 200 kilowatt. If the ambient temperature is 25 degrees centigrade, so atmospheric temperature T0 is 25 degrees centigrade. That is 25 plus 273, 298 Kelvin. What is the entropy generation in the turbine? So now if you look at that, so the enthalpy at the inlet, so enthalpy at the inlet is superheated. So this is the inlet condition. Inlet. Outlet is saturated vapor. So this is the outlet condition. So that means this is your H1. So this is your H2. So this value is your H2. Now if you look at the work output, H1 work output is, so if you apply the steady flow energy equation, so work output must be m dot into H1 minus H2. Let's check what is the work output that you get it. M dot is 16 kilogram per second. H1 is 3625.34 minus 2584.63 into 16. So how much you are getting is 16,651.36 kilowatt. This is what you are getting. So what is the work output? This is the work output. So there is a difference. So that means the difference will be going out as a heat. So maybe this is the work output calculated from enthalpy drop. So it is not matching. So enthalpy drop calculated from the given data is not matching with the work output given. That means there must be a heat transfer. Since the value of calculated value is more than the work output, that means the remaining part of the work must go out, remaining part will go as a heat. So there is a heat loss. So heat loss. So the heat loss will be calculated from this difference. Maybe otherwise you can apply the steady flow energy equation, in minus out, so or in equal to out. This is a steady flow. Energy equation. So energy in is m dot h1, kinetic potential energy neglected, will be equal to Q loss plus work out plus m dot h2. So now m dot h1 is 16 into 3625.34 Heat loss is what we wanted to calculate. Work output is, everything is in kilowatt, so you can substitute in kilowatt plus m dot into H2 2584.63. So heat loss. Okay, so heat loss is given indirectly, explicitly not mentioned in the problem. Okay, so sometime people may go without considering the heat loss. So if explicitly heat loss is not given, you just calculate the given work output is matching with the enthalpy drop. So if it is matching, then there is no heat loss. If it is not matching, there must be a heat loss. That is why it is mismatched. So energy must be balanced. The only way to balance is by a heat loss or a heat gain. Depends on the situation. So now we just $451.36. So now we apply entropy balance to find the entropy generation in the turbine. So next we go for entropy balance for turbine. Entropy in minus entropy out plus entropy generation equal to rate of change of entropy inside the control volume. And this will be 0, rate of change of entropy, because turbine is a steady flow device. Now we write the entropy in. So entropy in, this is the entropy in S1. This is your S1. So this is the S2. S2 is equal to Sg at 10 kPa outlet pressure. Then heat loss. So how do you get the entropy transfer through a heat loss? So you please, what you understand is, so we take, this is the turbine. So there is a heat loss. So heat loss is going to an atmosphere which is at, atmosphere is at 298 Kelvin. 298 Kelvin. So this is the turbine. Now we assume that entropy loss from turbine due to heat loss equal to entropy gain by atmosphere. So when the turbine is losing heat to the atmosphere is gaining entropy, turbine is losing entropy. Since we don't know the turbine surface, earlier problem, the surface at, from the surface temperature at which the heat loss is given, so we could get the entropy loss due to the heat loss. So this entropy gain is heat loss by 298 Kelvin. So heat loss will be 451.36 kilowatt. 451.36 by 298. 460. So this is 1.515 kilowatt per Kelvin. This is the because heat loss is given in terms of kilowatt, and irreversibility asked is also kilowatt per Kelvin. So everything you can put in kilowatt per Kelvin. So now we can go for this enthalpy. There will be an enthalpy in 1, 2. So m dot S1 not m S2 entropy generation inside the turbine. Work output is there, but work output does not contribute any entropy change. So entropy in will be m S1, entropy out will be m S2. Then the heat loss by 298 plus entropy generation equal to 0. M is 16. S1 we just get. S1 will be 6.9028 6.9028. So this is in kg. This will be in kilojoule per kg Kelvin. Mass flow rate is kg per second. 16 kg per second. So this is kg per second. So you get the product kilowatt per Kelvin. Okay, so that unit must match. Then 16 into S2. S2 is 8.1501. 8.1501. 8.1501. So here also the same, the kilojoule, kilogram per second, kilojoule, kilogram Kelvin. So the unit will be, this also will be in kilowatt Kelvin. Plus, minus the heat loss by 298, 1.515 kilowatt entropy generation. So now you get entropy generation. So it is 21.47. So let's see how much digit rounded up to 2 decimal place. So 21.47 kilowatt per Kelvin. So entropy generation is 21.47 kilowatt per Kelvin. So you should have a proper systematic understanding, without which this kind of problem will not be solved that easily. Okay, so now we go to question number 5. So an insulated rigid closed tank of 2 meter cube internal volume. So insulated volume is 2 meter cube, contains a saturated vapor mixture at 200 degrees centigrade. So maybe a liquid and mass of gas, mass of liquid. So the quality of the mixture, so dryness fraction is 0.75. The mass of the mixture in the tank in kg. So now we know that the mass of the mixture, so volume by mass of the mixture is the specific volume. This will be equal to Vf plus X into Vfg. So this M is the mass of gas plus mass of the liquid together. V is known, M is known, Vf is known at 200 degrees centigrade because Vfg is also known, dryness fraction is also known. We get the value of. So V is 2 meter cube by mass in kg. Vf will be 0.001156. 0.001156 plus dryness fraction is 0.75 into VFG. VFG is directly given 0.12620. .88. So the mass will be 20.88 kilogram. Rounded off to 1 decimal place. So then 20.9 is the answer for this question. So thank you for watching this video. So if you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE Mechanical Engineering subject. If you want to join for the GATE 2026 video course, please contact this number. You can also go and see in the website. Thank you.